Alright, so we finally made it to limits. And instead of trying to give you a mathematical definition of a limit, I'm just going to show you some examples. I'm a very visual learner, so seeing examples helps me a lot. So I'm going to draw a function out here. So I drew the axis, and I'll draw y equals x squared. And this function is going to look something like that. It's going to look like a parabola. And in this function, for every value of y, we have a value of x. For every value of x, we have a value of y. So what a limit is going to do, it's going to zoom up really close to a point on the function and see, based on the surrounding points, where the function is headed around that location. So when you have limit problems, they're going to look something like this. We're going to write lim for limit, L-I-M, the limit of the variable of the function. So in this case, y equals x squared, the variable is x. The limit as x approaches some value. So for an example, I'll just put 0. The limit as x approaches 0 of the function, x squared. And what this really means is we're going to zoom up on the function around this point, x equals 0. So we're going to zoom up onto the function, and we're going to look at the surrounding points and see what values they are and see where the function is heading. So to do that, we can do it manually at first. So we can say, all right, we have x squared, and we want to know when x equals 0 what this value would be. And in this case, it's really easy. You could just plug in 0, and you could get a value of 0. But limits become useful in cases where it's not easy to plug something in. I'll show you some of those examples later, but right now we're just for the sake of understanding limits, we're going to plug in some values that are close to 0 but not 0. So let's plug in 0.01. What are we going to get? We're going to get 0.00, I think 4 zeros, and then a 1. And then on the other side, we could think negative 0.01. We get the same thing. We could plug in 0.0001 and then find the value and see that it just gets closer and closer to 0. I'm not going to do this a whole lot, but you could write a program and just plug in values that are closer and closer to x equals 0 and then calculate the output. But the point I want to make is, when you're looking at a value, considering a value with limits, you are going to look closer and closer at the points to see what values are coming out, to see, okay, it's approaching a certain number. And whenever you have limits, the first thing you should do is just plug it in and see if you can get the right answer. So this is going to be our first limit. The limit as x approaches 0 of x squared is just 0 squared, which is just 0. You can just plug it in. All right, let me pull up my notes. See where else we want to go. Okay. So let me show you an example of where this would be useful. So let's say instead of having some nice function like y equals x squared, some nice continuous function, we have a step function. I'll get a blue marker for this. So let's say we have the function y equals, we'll say 2x when x is not equal to 3, and then y equals 0 when x equals 3. This is a weird step function, but we'll draw it out. So y equals 2x when x is not equal to 3. So we'll draw our 2x line. So that wasn't quite steep enough. We'll draw it again. And so we have y equals 2x for every point except x equals 3. So in this case, we'll draw a little hole right at x equals 3. Now let's say I want to find the limit of this function. Oh, I guess I should put a a dot here. The limit of this function as x approaches 3. In this case, it's only defined, well, it's defined everywhere, but it's not defined on the line 2x at x equals 3. So let's find the limit. The limit as x approaches 3 of y, which is really 2x in this case. So as we can see in the function, when x equals 3, it's actually 0 because of how we defined it. But if we want to find the limit, we want to look at the points around our point of interest. We're going to see it approaches a different value than what we defined. So here the limit as x approaches 3. In this case, we can just plug it in, and we get 6. And through this analysis, we found that even though we defined it to be different, the limit of this function approaches 6 as x approaches 3. And now you can also have cases where you have a different value for the limit based on which direction you're looking. So I'll do a different step function for this to get across this point. So let's say we have y equals, we'll keep 2x as an example. So 2x when x is less than 0, and we'll say x squared when x is greater than 0, or greater than or equal to 0. So let's graph this one out. So we have when x is less than 0, so on this side, the function is going to be 2x, so steep slope, and then when x is greater than or equal to 0, we have x squared. And let's say, actually, let's say not equal to 0. Let's put a hole here. So right at the origin, there's a hole. Now, what is the limit when x approaches 0 of this function y? Actually, I'm going to change this. Instead of 2x, we'll say 2x minus 2. So this will actually bring the limit down a little bit so it does not go to the same spot. All right, so now we have the limit as x approaches 0 of y. And now if we look at the left-hand side, it's going to approach a value of 2 because that's where it intersects. On the right-hand side, it's going to approach a value of 0. So in this case, the limit as x approaches 0 of y would actually be undefined, UDF. So what do we do with this? The trick that we use for this is actually we take the limit from the left-hand side or the right-hand side to find a value. So in this case, we can say the limit as x approaches 0, let me make sure my laptop's still plugged in. All right, the limit as x approaches 0 from the right is going to be just the right side of the function here. So we have when x is greater than 0, it follows this rule, 2x minus 2. So when we look at it from the right, we have this little plus sign here. Limit as x approaches 0 from the right of 2x minus 2 is -2. Or sorry, I chose the wrong one. When x is greater than 0, it's x squared. I was thinking that doesn't quite seem right. Okay. Limit as x approaches 0 from the right of x squared is 0. So that's one solution. The other one, limit as x approaches 0 from the left, and we have to use the left-hand side. Oh, sorry, the left-hand side, 2x minus 2. We plug it in, and we find it approaches -2. So this is our first example of a scenario where limits are valuable in identifying really what this function is doing at this weird point where there's a hole in the function. And you can consider the limit overall, or you can consider the limit from the right or the left. And again, we're just trying to think where the line is heading to if it continued on with the function. That's really all a limit is doing. All right. Okay, so there are some scenarios where limits do not exist. We talked about one where there's a break in the function. That one we would really say the limit doesn't exist unless you were looking at just from the left or from the right. All right, so we're going to look at an example where the limit does not exist. Let's consider the function y equals 1 over x. So on the right-hand side, this function is going to look like this. On the left-hand side, it's going to look like this. So what if we take the limit as x approaches 0 of this function? Limit as x approaches 0 of 1 over x. Here, it depends on which side of the function you're looking at. If you're looking at the left-hand side, the negative numbers and getting really close to 0, it approaches negative infinity. If you're looking at the right-hand side, you can see it's approaching infinity. So in this case, the limit is undefined, or the limit does not exist. So how would you solve this? Like we did before, you would have to look at it on, you would just have to pick a side and evaluate the limit from the left or the right to get a value. But the limit of this function as a whole does not exist when x approaches 0. And a lot of the problems with limits are going to deal with situations where the function, when you plug the number in, is going to get some weird value or get 0 over 0 or infinity over infinity or something along those lines. In this case, we can't just plug it in because 1 over 0, you can't divide anything by 0, so it's undefined. All right, so there are limit rules that you can use when manipulating equations with limits in them. And none of the rules are that surprising, but there's 5 rules we want to go over. So there's the addition rule. So limit as x approaches a, I'll just write a here because it could be any number, it could approach anything, of f of x plus g of x. And again, I'm just putting these as placeholders. It could be any function or it could just be a number or something. But we're taking the limit of this addition. That's going to equal the limit of each part. So what we're saying is that you can split this apart. You can move the limit really inside this addition and have 2 pieces with the same limit added together. Same thing with subtraction. So if this was a minus sign, you could do that. And also the same thing with multiplication and division. So that's equal, or if you multiply these together, you can move the limit operator inside and outside of these situations. And then last but not least, you can also move a constant out. So if you had the limit as x approaches a of c times f of x, this is the same as c times the limit as x approaches a of f of x. So to put this in a specific case, you could say the limit as x approaches 2 of 3x squared is the same thing as 3 times the limit as x approaches 2 of x squared. This constant can move in and out, if you so wish. Let's see. So, and then there's another one with the power law. So if you have the limit as x approaches, let's say 7 this time, of 2x minus 3 squared. This is the same thing as the limit as x approaches 7 of 2x minus 3 squared. So we already discussed this a little bit. We said the limit as x approaches 0 of 1 over x is technically undefined, but moving forward we are going to assume that it's coming from the right. So we are going to say this is actually equal to infinity, and this will come in handy actually, let me not do that one. Okay, so we're going to consider the limit as x approaches infinity of 1 over x. So this is going to be one of our first really limit tools in our tool belt when we're solving some limit problems. Limit as x approaches infinity of 1 over x. You can imagine what this is going to be equal to, because the larger the number is that you plug into x, the smaller the entire value is going to be. So the limit as x approaches infinity of 1 over x is 0. It'll never reach 0 no matter what number you plug in here, but as you continue on to infinity, it's going to get closer and closer to 0. So that's why we say this is equal to 0. And this will be very useful. The other one that you can also consider, which we talked about it earlier, was the limit as x approaches 0 of 1 over x. And even though it's really undefined, a lot of times if this comes up, we consider it coming from the right, and we say that this is equal to infinity. So that'll come up a fair amount later, but really this top one is one you want to remember with these problems. All right. So now we're going to talk about something called the Squeeze Theorem. This doesn't come up very often, but it is a tool to help you solve a limit when it doesn't seem like it's easily solvable. So the example that I have is the limit as x approaches 0 of x squared times cosine of 1 over x. Oh, sorry. The limit as x approaches 0 of x squared times the cosine of 1 over x. So if we plug it in, we'd get 0 squared times cosine of 1 over 0. So it would either approach infinity or negative infinity. And if you remember with cosine, if you bring it out to infinity, it's undefined, because cosine constantly oscillates between 1 and negative 1. So no matter how far out you go, it's never going to approach a value. It's always going to oscillate. So you really can't do this limit just by plugging it in. So what can we do with this? Because we know that this has to approach some type of a value when you multiply x squared by it. X squared is going to get really close to 0. This cosine term isn't going to go away. So you can use something called the Squeeze Theorem. And the Squeeze Theorem says if you have some function that you're not quite sure what the limit is, and you know that it's greater in value than one function and less in value than the other function around this point, then if those two functions that are on the outsides of this function approach the same value, then this has to approach the same value as well. So that's a long way to really describe the solution there, but I'm just going to show you the solution. So we have this weird equation, but let's start with cosine of 1 over x. So just consider cosine of 1 over x. So like we said before, cosine oscillates between 1 and -1. So you can say that it is true if this is, or let me get the other direction. This is going to be less than or equal to 1 and greater than or equal to -1. So we set up an inequality just starting with the term of interest here, cosine of 1 over x, the confusing one. And now let's multiply, because we have an inequality, we can multiply each piece by something as long as every single piece is multiplied by it. Let's multiply everything by x squared. So we are going to multiply the entire thing by x squared. So x squared times -1 is, x squared times -1 is -x squared, which is less than or equal to x squared cosine of 1 over x, which is less than or equal to x squared. And here we have the function we were originally starting with, that we did not know the limit. So in this case, we know that this inequality is true, and if we take the limit of this side, and it matches up to the limit of this side, we know that that value is going to be the same thing as the limit of this. So what is the limit as x approaches 0 of -x squared? Well, we can just plug it in, and we get -0 squared, or 0. Similarly, limit as x approaches 0 of x squared is also 0. We just plug it in, and it gets results in a value of 0. So therefore, because this is in between these two functions, the limit as x approaches 0 of this previously difficult problem is also 0. And that's the squeeze theorem. We're squeezing our function of interest in between two different values that we can evaluate, or two different functions. I haven't seen this come up very often in other areas, but it's just a tool to have in your back pocket if you happen to find yourself in a situation where you know that the function you're looking for is less than and greater than two different functions. So don't stress too much about remembering this or knowing when to do it. Sometimes it's really hard to know when is the most appropriate time to use the squeeze theorem, but just a tool to have in your back pocket. And that is all I have for this video, and we're going to do 2 more limit videos, just going through some practice problems, getting used to using limits, and then we'll move on to derivatives after that.